Hi, everybody. Sorry about the delay there. How are we all doing tonight? It is once again time for Chem 161. Just some administrative stuff to talk about really quick before we get started. So you can see at the bottom, due dates are coming up. Lab number 1, which is the glassware and sugar density percentage in soft drink beverages lab. That is due tonight. That is a soft deadline. Last call will go out tomorrow at some point. I will just send an email that says, today is last call. Turn in by tonight. The deadline is, it closes. So finish it by tonight if you can. If you absolutely need more time, you do have tomorrow to do it. Just don't forget. You'll get one more reminder. Quiz number 1, same thing. It's due on Thursday. Quiz number 1 deals with the entirety of Chapter 1, and it's only Chapter 1. So you don't have to worry about anything that we cover today. That will all be on quiz number 2, which will be posted when we finish Chapter 2, which probably won't be today. So without further ado, let's get ready for chemistry. Here we go. Chapter 2 is about philosophy, sort of. I mean, it starts with philosophy. It's basically the history of how all of chemistry was formulated. We don't cover this in 140, so this is new. We are going to touch upon a few things that are kind of weird-looking calculations, and the reason that they will be weird is because we are starting from a foundation of nothing, more or less. How do you find the chemical formulas of things when you can't see them? That is a monumental task, and there's a reason that it has taken, I would say 1,500 to 2,000 years to get this far. What we cover in this class was the frontier of science in the 1700s, 1800s, even in the 1900s. Like, when we get to quantum mechanics, that's going to be like 1910, 1920, 1930. So, like, this stuff isn't even 100 years old, and here we are learning about it in a very basic class. And that's sort of just how science works. Like, eventually the stuff that's groundbreaking today will be a first quarter textbook. Just food for thought. So, let's get started. Let's talk a little bit about how this worked here. So, around 400 BCE, we have this guy. He must have been important. They made a statue out of him. His name was Democritus. Democritus was a philosopher, and he thought about matter. And he thought to himself, well, the legend that I heard was that he was at the beach one day, because in Greece, there's just beaches everywhere, right? And he ran his hand through the sand, and he was looking at the sand particles and thinking, you know, I bet there's some smallest particle of sand that if you subdivided it further, you wouldn't have sand anymore. You'd have something else. And back then, the philosophy of, like, the elements being, like, fire, earth, air, and water was dominant. But there was also evidence that there were other things, and it was all sort of starting to congeal and bubble together and stew in the pot of knowledge. He called the smallest particle, this theoretical thing that he thought of, atomos, which means, like, a little tiny piece. That smallest particle would be what we would refer to as the atom today. Now, along comes Plato and Aristotle, also important, also have statues. They thought they thought Democritus was wrong. And the way that they determined this was they said, well, why would you only be able to split something down to some point? Why not cut that in half and then cut what's left in half and cut what's left in half and do that over and over and over and over again infinitely? And so they decided, and I use the word decided specifically there, that matter could be subdivided infinitely. And that it was silly to have a smallest particle. Now, if this were a game show today, then Democritus would be the closest to having the correct idea of the atomic nature of matter. But the real moral of the story is that Greek philosophers are stupid. And the reason for this, we're going to draw a big fat X through Democritus too. Even though he was mostly right. These three philosophers committed what I would call a scientific sin. And that scientific sin was they didn't do experiments. They didn't do the scientific method. What they were doing was called philosophy. So nobody did any experiments to verify their hypotheses. This was all just thought experiments. So what they were doing was not science. Philosophy is a set of definitions that we establish as truths because we have to start somewhere. And from there, then we do analysis and assessment, and then we can do the scientific method. But they tried to skip and circumvent that and determine a truth without any evidence. That doesn't fly in science, but it does serve as two things. One, it serves as a good thought process to later do the scientific method. And that's what Dalton does in the next slides too. The second thing that it does is it provides an important sort of understanding that you can claim whatever you want to, but if you don't have scientific facts and observations to back that up, then you're just spouting hot air. Okay, so we're going to try very hard in this class to stick to only observable scientific facts because these guys couldn't observe these things. They didn't possess the technology to subdivide molecules down to the atomic level or further because we barely have that technology today. Those are called super colliders. You may have heard of CERN or the Large Hadron Collider. Those are things that we use today, and they're very, very advanced compared to whatever tools they had in prehistory. How long did this theory last? The theory of, oh, there are 4 elements, fire, air, earth, and water. 1700s. Now, people had discovered other elements, but things like carbon and iron and stuff, they decided that, oh, well, maybe that's Earth with a smattering of water or whatever. And if you play a lot of video games that deal with alchemy, you'll see alchemical symbols representing these things. So there's the alchemical symbols for fire and water, and they're like triangles with lines through them and stuff like that. And then we assign planetary symbols to other elements too. And there's all that garbo that's aesthetically really pleasing, but scientifically means nothing. It wasn't until Dalton came around that he really started to look at this stuff in more detail and started proposing experiments. So John Dalton and Isaac Newton, around this time, so late 1700s or so, they used Democritus' proposal as a starting point. And they said, okay, if this is true, let's try and find information that supports this. And so what Dalton did, he did a series of experiments that pointed to evidence that matter was indeed atomic in nature. And he created, more or less, what we'll call his 5 points of atomic theory. Now, because this was very early science, relatively speaking, this is, again, 18th century, so over 250 years ago at this point. A lot of these principles were tested and observed, but they didn't show the complete picture. And as we go through chapters 2 and 3, we're going to slowly we're going to peel away more layers of the onion to discover what the actual structure of atoms is. And we'll talk a little bit about some experiments that led to those conclusions. So here's the first point of atomic theory. Dalton said that all matter is composed of atoms, and that those atoms are the smallest units of elements that can participate in chemical changes. All right, what does that mean? In other words, an atom is the smallest particle that can perform chemistry. Chemistry being the transformation of matter from one compound to another. If you subdivide an atom, you get its parts, and he didn't know what those parts were because he didn't really have a way to observe them. Those parts can undergo other types of reactions, but they're not chemistry. Those are nuclear physics reactions. So he noted that there may be something that exists past this point, but if there is something that exists, it doesn't do chemistry. It does physics. The next thing he said is that all atoms of a given element are identical to one another. So all copper atoms are exactly the same, and his rationale for that was, well, all copper samples that I have react the same. If I burn them in the presence of oxygen, I always make this black kind of crud, which was copper oxide. All iron atoms are all the same. If I burn them in the presence of oxygen, I get this orange crud, which is rust. And he could not do an experiment that used a given element and get a different result. He got the same result every time. And so he said, okay, well, all of atom X are identical. There must be something in an atom of a different element that causes it to differ somehow. Now, he's kind of vague here. He writes in some way because he didn't understand what that was at the time. The technology and the theory didn't exist. So there must be some component of atoms inside them that makes them differ. Now, we know what that is today. That's protons and electrons, and to some extent the neutron. But he didn't know that back then. Other experiments that were done, and we're actually going to look at some of these experiments later, is that whenever you make a compound, compounds are composed by elements that combine in whole number ratios. In other words, you could do this with a compound, so you could combine carbon and oxygen. You could combine them in a 2-to-1 ratio, but you could not do this. You could not have half of an atom. So this is not allowed. The ratio must be whole numbers, and that number, the numbers do not have to have 1 necessarily. So C2O3 would be allowed. And then the last statement that he made was that you can't change one element into another element. Elements are immutable. So an element cannot change into another element. So all atoms of copper are stuck as copper. They cannot change into iron. They cannot change into tin. They cannot change into gold, which made a lot of alchemists unhappy because that was the Holy Grail, finding that philosopher's stone that would turn lead into gold. All that happens in chemistry, in a chemical reaction, is that atoms get rearranged and you make a new compound out of the constituent atoms that were there before. Now, of these 5 things, some of them have held up to the test of time today, but others have not. For instance, number 2 up here. We know that this isn't true anymore because we know of the existence of isotopes. We'll talk about isotopes later. This one is also not true if you ignore the word chemical. Atoms can be changed from one atom to another, but it requires a nuclear reaction. So, again, this Dalton's atomic theory is a blueprint, but it is not the schematic by which all science is bound to. And a lot of these ideas paved the way for us to find out more stuff about atoms later. What we're going to do now is we're going to look at number 4 here. We're going to look at some experiments called the law of definite proportions and the law of multiple proportions and show how they started to determine, oh, we can make compounds out of these things. Here's how we get the ratios of the atoms, and then what we can do with that later. So these 5, I guess we'll say lemmas or statements, help us explain a lot of things for reactions that occur in very controlled conditions. So for example, on the screen here, I have copper and oxygen. Here's my copper right here, and here's my oxygen. And if I allow these to react, either by like importing heat or just waiting, what I will observe is that I will get a new compound over here that incorporates the oxygen into the copper. The properties of these compounds are different from one another, and they can be tested. For example, copper will melt at a fair temperature because metals have melting points that are average, we'll say, so like a few hundred degrees Celsius. But ionic compounds like copper oxide have a much, much, much higher melting point. So you could test whether these are the same, not just by looking at the color, because they're obviously different, but by trying to heat it. One will melt much earlier than the other one, and that's the metal. Now, you could reverse this. You could go back and forth. One direction is usually much easier than the other. And so experiments found that, oh, if I have this black powder that formed from copper being exposed to oxygen, if I heat it or apply electricity or do some specific thing, maybe in the presence of hydrogen, I can rip that oxygen off and I get the copper back. In both of these cases, chemical reactions are occurring. Now, very importantly, if I'm doing this reaction in a sealed container, nothing can get in there, and nothing can get out. So all that's happening, he concluded, was that, okay, the atoms must be just rearranging how they are bonded to each other. The amount of matter that's in there remains constant, and so this satisfies the conservation of mass. Matter is not created or destroyed, and by extent of that, the atoms aren't changing or disintegrating into pieces or annihilating or anything like that. Now, if I were to try and break down a simpler substance, like just the copper, and I do stuff to this, I can't. All I end up with is copper. So if you have a substance that can't be broken down, odds are that it is just an element. Now, particularly with metals, this was obvious for them to do. They could get the metals to a point where all they could do was atomize them and turn them into a liquid or a gas, but they wouldn't do anything else. Like they would play it out on the surface of the container or whatever, but they'd still be that material, and then you could react them later. One particular stumbling block that a lot of people had trouble with was water. Water is very stable. It takes a lot of energy to break water into its constituents. Substances. So for the longest time, people thought water, which was one of the 4 fundamental elements, fire, air, earth, and water was an element. And it wasn't until somebody decided to do electrolysis with a high current electrode that they found, oh wow, water can dissociate into hydrogen and oxygen, but I can't dissociate those further. So water is not an element, water is a compound. And all of these experiments and all these thoughts came about from atomic theory. So you could see how atomic theory was kind of the first big step. We planted the flag and said, okay, this is where we're going to start from, based on philosophy, kind of because we had to. But then we started doing experiments, and we could create the atomic theory on a more stable foundation. All right. I'm not going to test you on who Proust is. Dalton is important because the 5 postulates are very important for the foundation of chemistry. But beyond this, we're just going to talk about the laws that other chemists came up with. So the first one is called the law of definite proportions. And it states that the ratio of masses of elements is the same in any sample of a specific compound that you acquire. So if I get a compound that has carbon and oxygen in it, and I decompose it, it doesn't matter where I acquired that compound from, I'm going to get the same result every time in terms of the ratio of masses. So we're going to look at C and O together, a carbon and oxygen compound. But they were doing things with like copper and oxygen, or rust, which would be iron and oxygen. And no matter where you get the rust from, the result was always the same. So let's look at an example of this, because the theory sounds kind of nebulous here. But when we do an example of this, it'll make sense. So what we're going to do is we're going to take compounds that contain carbon and oxygen. We're going to decompose them. And these are the results that we get. So I have sample A, which came from city A or whatever, or mine A or whatever. And then sample B came from aquifer B or plains B or whatever. They came from different places, and they were different masses, and I got these results. So what we're going to do is we're going to take the ratio of masses. So I'm going to do this ratio. I'm going to do mass O to mass C. Just because I'm going to put the bigger number on top, that'll give us a whole number, or like a number greater than 1 at least. So let's look at sample A. So for the mass O to mass C, that would be, sample A is 1.55 grams of oxygen and 1.16 grams of carbon. If I do the math here and I go 1.55 divided by 1.16, I get this result. 1.336, which we'll do sig figs, so 1.33 grams of oxygen for every gram of carbon. So if this result is true, then for any sample I get, I should get the same ratio. So let's look at sample B. We'll do the same process. 3.33 grams of oxygen to 2.50 grams of carbon. And we'll put it in the calculator, and what do we get? 1.332, which when I round to sig figs, I get the same result. And so the results showed that, okay, if I do this process for this compound, this specific compound, whatever it ends up being, and I can verify that this is the same substance, I can use this to test other substances that may be similar. Because if I get another compound and I get a different result, I know that it is not the previous things. I lost a grams here. So this is sort of a test that you can do. Are these two things the same? And if they have the same ratio of masses, then they concluded that, yeah, they should be identical. And for the most part, this works. We'll talk about when it doesn't work later on. All right, let's look at this third sample here and see if it is the same. So is C the same as A and B? So we got 10.81, oops, not 10.81. That's not what I meant to do. So for sample C here, we got 10.18 grams of oxygen and 3.82 grams of carbon. And you should be looking at that and going, yeah, there's no way that's going to be 1.33. And what I get is 2.665 to 1. Is it the same as this? We know for a fact that it's not. There's twice as much oxygen in this sample as there is in the previous samples. Now, our conclusion could be that, well, wait a second, this number is useful to us in some way. Because if I look at these two, what's the factor that separates them? It's a factor of 2. And so I could conclude here that, okay, well, this compound isn't the same as the previous one, but maybe its formula has twice the number of oxygen in it. And that's where the law of multiple proportions comes in. And what that says is that if I compare those ratios that I just got, I will find some number that is a small whole number that relates them. That's what this is saying in more words, basically. And so we saw earlier that the difference between these ratios was a factor of 2. And so we could conclude then that these compounds are related to each other in a way that there is double whatever the element was that we were using the ratio for, which would be oxygen in this case. So let's look at some data and do that. All right, there's our ratios from before. And we said that they were different by the factor of 2. So sample C is twice as much oxygen as samples A and B. And then from there, if I propose that, okay, let's assume that the first one is CO. The second one must be CO2. Now, if we determine that the first one was CO2, if this was A and B, then that means that C would be this. Okay? Now, we know that this isn't a thing that exists today, so that this is likely the correct answer. But back then, people had no idea. They had no mass spectrometer or particle accelerator or anything like that to analyze atoms at the smallest level. They were trying to figure this out because this was all new. So by putting these two laws together, the law of definite proportions and the law of multiple proportions, we can figure out ratios and then propose formulas and then work from there. Okay? So again, this is just the foundation of where all of the chemical formulas that we have derived today came from. And then later on, as technology improved, we got another way to do that, and that's called mass spectrometry. And we'll talk about that later on. All right, so what I want you to do, I'm going to give you these sample problems to try. I want you to look at compound X and Y, which are compounds of iron. And I want you to first determine the ratio of one element to another. You get to pick which one you put on top. I want you to tell me, are they likely to be the same compound or are they different? And then what is the ratio between them? Okay, give it a shot. We'll go over the answers in just a second. I know it's pretty quiet in here, but when you get an answer, type your formula in the best you can in the chat. All right. 1 more minute to finish up. We'll go over the answer. All right. So let's do that. Right there. All right. So for the first one, we'll call it X. Oh, that's what it's called. I'm going to do mass of iron to mass of oxygen. Excuse me. And so we'll say 47.13 grams of iron over 20.26 grams of oxygen. And the ratio I get for that is I get 4 sig figs here, actually. So let's do all of them. So there's my ratio, 2.326 to 1. And then we will do sample Y, which is the same definition. So mass of iron to mass of oxygen, 35.63 grams of iron divided by 10.21 grams of oxygen. This should be much larger of a ratio. And so we would conclude that these are not the same. Now, if we observe that they're different, which we did, we need to find the ratio between them. And so now what we want to do is try and find out what the relationship is between these. And it might not be times 2. So what we're going to do is go like this. And this should be the number that I multiply by to get here, right? Times whatever. And just looking at this, I'm going to guess it's like 1.5. But let's see, what do I get? Yeah, I get 1.500. Now, I'm going to call it a multiplier. Later on, we're actually going to call it a multiplier. But remember that if I were to multiply 2 atoms by this number, I would get a fraction, right? So I can't do something like that. So I'm going to have to multiply both sides by 2 here. And so what I would end up doing is, so multiplier would be 1.5. So if I had iron to oxygen here, and I multiply just the top by 1.5, I'd get a fraction. So what I'm actually going to do is I'm going to multiply both of these by 2, because that will get rid of my fraction. And that's how you get that 3-to-2 ratio that people are quoting in the chat. So the conclusion that we would draw is that if this one is times 1.5, then we can make an assumption that the first compound might be this. And then that the next one should follow that ratio. Something like that. Because there's 1.5 times as much iron in there. Now, do these compounds exist? Maybe not. I'm just using numbers. But the point is that this is the sort of process that we can go through to slowly identify chemical formulas. All right. That's kind of all the work that we're going to do with the law of law of definite and then multiple proportions, is that sort of thought process. From here on, what we're going to do now is we're going to use that information later once we've talked about the pieces of an atom. And we're going to use that to do what is called elemental analysis and empirical and molecular formula calculations. Most of that stuff we actually sort of push off until... I don't think we do it in this class. Maybe we do it at the end of chapter 2. We do very rudimentary calculations, but then we do a lot of this stuff in 162. So, if you remember all of the end calculation stuff from Chem 140, you can see how this is sort of trying to guide us towards that. Oh, excuse me. We are going to do a few calculations towards the end of this chapter. All right. Let's talk about the pieces of the atom. For this, what we're going to end up doing is I'm going to show you a bunch of videos of these experiments so you can actually see the experiments going on. But the first thing that people tried to figure out was, okay, if there is some difference between different elements, and that difference is at the atomic level, what is it coming from? And the only real option they had was to just try stuff. What can we do to split the atom apart? And here's what they came up with. The first discovery was the cathode ray tube and the electron. And so this is what a cathode ray tube looks like. Late 1800s, they took this tube that they had removed most of the air from using a vacuum pump, put electrodes at either end, and then connected the electrodes to a battery. Yes, batteries were around in the 1800s, believe it or not. Now, this device does the following. If I apply a current to both ends of these plates, so here's my plate and here's my plate, and there's nothing inside this tube, so it's just empty. Like there's no air or anything at all. Then what ends up happening when I apply the current is that the circuit connects by jumping across this distance. Now, for a long time, nobody knew what electricity was. They knew that something had to be moving, because otherwise how would the electrical process go? But this right here, this like white block, This is a fluorescent screen that when a particle bonks into it or collides off of it or passes through it, you end up observing a glow. And so this showed that there was some object that was going through the tube. And more importantly, they could show that that object could be manipulated, because what ended up happening next was they exposed it to a magnet. And when you use a magnet, what ends up happening is that the particles of whatever sort that are going through here get deflected either towards or away from the magnet based on what orientation of the magnet is used, either north or south. So what I'm going to pull up here is a video of what this looks like. And I need to capture the video really quickly, so give me a second. Window capture, that's not the window, that's live split. Cathode ray tube, there we go. Alright, let's see what we've got here. Oh, that was perfect. Okay, so here we go. So, this guy's going to talk, but I'm going to talk over him because I've muted him. This is what the cathode ray tube looks like. You can see on the sides here are the electrodes, and then this is the battery that's connected to it. That white box right there is the fluorescent screen that the current is going to pass through. The beam is aimed so that it goes through the middle of the screen. Like the screen is in the middle and not behind it. Now you can see that the beam passes right through it in a rather straight line. And then when a magnet is applied to it, it will either deflect towards it or away based on which orientation the magnet is pointed. So there's one orientation, and then when he spins the magnet around, which he'll do in a second here, it should deflect in the other way. Now, why is this important? People didn't know what charged particles were at the time, but what they did know is that things that were charged moved in magnetic fields. For example, like you can coil a wire around a magnet and you get interesting effects. I forget all the physics behind this, but it was known that magnets and electricity interacted with each other. And so what that experiment shows is that, okay, this is definitely electrical in nature, and then by seeing it deflect and seeing it pass through this screen, they could conclude that a particle was responsible for the electricity. Oops, I didn't mean to click on that. They called that particle the electron because it was the particle responsible for electricity. Yeah, the right-hand rule. I know of that, and I know that if you like put a magnet with some orientation, it deflects on whichever direction your middle finger is going, or something like that. I've been told that the number one way that physicists injure their hands is if they have to orient the vector with their middle finger towards the right instead, because you get to turn your hand over. That actually did kind of like make my hand sore. Ow. So I'm not a physicist. I don't have to do the right-hand rule. All right. So we know that electrons exist at this point. 100 years later, or something like that. How many years later was this? Okay, not that many years later. It was like 20 years later or so. Excuse me. 20 or so years later, Millikan comes along and he says, okay, I know that electrons exist because my predecessors have identified them. I want to know more about the electrons. Can I figure out how much charge each electron has? Do they all have the same charge, or are they all different? And so he proposed this experiment. In this device, this sealed device right here, we have this tube that atomizes oil droplets. And what that means is that it tries to make the drops as tiny as possible, like this. Now, if the drops bonked into each other, they would coalesce into a larger drop. But the atomizer tries to make the droplets as tiny as possible. And the reason that he's doing this is he wants the drops to be very light in terms of their mass. The lighter they are, the less force of gravity will pull down on them. And that'll be important in a second, because what ends up happening is the drops fall through a little pinhole in the disk down here into a second chamber where we have ionizing radiation. What that means is that this X-ray right here is producing ions. And by producing ions, what I mean is the ionizing radiation is knocking electrons off of things and causing them to bounce around. Some of those electrons might actually hit our droplet. So if this is my droplet, I might catch an electron. If I catch an electron and it stays on the droplet, then now that droplet contains the charge of the electron, which means that I can manipulate it with other things that have charge, such as, say, a plate below it with a negative charge and a plate above it with a positive charge, which I can do by connecting to a circuit. Now I have the following scenario. This droplet wants to fall down, and the force that is pulling it down and causing it to accelerate in the downward direction would be its mass times gravity. But if I have a negative plate pushing it upwards, the force pushing this upwards would be equal to the charge on the electron times whatever the strength of this electric field is that I've produced. And so the electric field is just related to the current and the voltage of the charged plate. More importantly, it can be known. What this means is that, okay, these two quantities have to be equal but opposite. And if I know what the mass of each droplet is, because I can approximate that, I know the gravitational constant, I know how much current I'm feeding through the plate, I could solve for this. And that is the charge of an electron. So by doing all this crazy physics shit, Millikan was able to determine, okay, if there is a charged particle on here, I could solve for its charge. And if I get the same number every time, I'm onto something. And if I don't get the same number every time, maybe I get a multiple, then maybe a droplet is picking up 2 drops of charge, or 5 drops of charge, or whatever. But there will be some ratio that tells me how many electrons are on there if an electron has a fixed charge. And so he did this experiment, and what he determined was that this is exactly what happened. All right. I'm going to cover up the mass of the electron really quickly. What Millikan quantified was this. One electron has a charge of 1.602 times 10 to the minus 19 coulombs. A coulomb is a unit of charge. You can just think of it as how much positive or how much negative. Now, because electrons are negative, we just append this sign to the charge. Now, there was data available at the time that related charge and mass together, and so by using that information, eventually the mass of this particle that was used was published as this value, which is super, super, super tiny. So the conclusion that we draw is that by understanding that an electron is a charged particle that is mobile, because we could fire it through the cathode ray, and then trying to catch it on an oil drop and then suspending it in this apparatus here, we can learn a lot more about it. And so this is the sort of like experimental thought that went into discovering these things. Like, these are bizarre experiments, even looked at today, but they're totally fundamental to our understanding of atomic matter. So I do have a video of this one too, and we'll get it on the screen here. This is the good video version of this. I have a bad version that's like super... It's hard to see. There we go. Okay. For some reason, the pips weren't showing up here. We don't need all of that. So here we go. So now you can just see the experiment in action rather than a still frame. So, and there's going to be subtitles, I guess, because there is somebody talking. So here's the atomizer up here. This is going to spray all the droplets that then fall down here. There go the oil droplets. And eventually they will settle and fall through the hole, and then they just fall down. Now, if this plate is turned off and there's no ionizing radiation, they just fall straight down and nothing happens. But if we use an X-ray, we bounce electrons all over the place. If the plate is still off, the drops will still fall straight down because there's nothing pushing them back up. But now what we're going to do is we're going to turn the plate on and allow these to collect electrons. And here's what ends up happening. As we change the strength of the field, they start to accelerate in the other direction. Now, if you turn it to just the right spot, oops, we'll pause here, you can suspend an electron. Now, what this involved him doing was looking through this lens to try and see if a little drop of oil was floating there. And you could actually control the current very finely to do this. Now, this is just the math that I just showed you. So, mass times gravity is being opposed by the charge of the electron and the electric field. Now, if there's one electron, then Q is just going to be whatever its charge is times 1. But if there were multiple electrons, that Q would be whatever the charge is of an electron times however many electrons were on there. And so the common factor that divided out, just like we did with the law of multiple proportions, was the number that I showed you, which is currently covered up by the subtitles. And then we could calculate the mass of the electron by using this published ratio that they're showing at the bottom. Let me see if I can get rid of the captions. There we go. That was known and gives us the mass of the electron. There it is. So this number, I don't actually know where this comes from. This is a physics phenomenon. It's called the mass to charge ratio, which you can look up if you're more interested in it. But I'm not going to test you on this. I'm just going to test you on what did Millikan's oil drop experiment discover. And the primary thing he discovered was this right here. Charge of an electron. And then from that, other people use this number along with Millikan to get this number. This is the important one. All right. All right. So that was enough to figure out the presence of the electron. If there was a negative part to an atom, then there had to be a positive part, because otherwise all atoms would be negative and they would all repel each other. Because just like the electron repelled the negative plate in the oil drop experiment, matter should do that too, but it didn't. So that meant there must be some positive part to it. We know about that being the proton, but in the next slide or two, what we're going to show is that they had some other ideas. And we're going to cover those ideas when we get back from the break. So let's put the break timer up here. I will start the timer. We'll get a 10-minute break. We'll get some more Metroid music going on. And I will see you in just a little bit. Ah, that's close enough, right? All right. Yes, welcome back for the thrilling cliffhanger. What could the proton be? Nobody knows. Well, nobody knew at this point, anyway. Welcome back. Let's talk a little bit about which Metroid planets I'm using Metroid Prime. I just pulled one up. I'm not super happy with the quality of that one, but it does sound a little different to me. Let's talk about the proton. So we're going to go through a few models here, and they're all wrong. Here's the first model. This is called the plum pudding model. The plum pudding model is bogus. Here's what they thought positive charge was. If electrons are these little guys here that are floating around that have a negative charge on them, then this giant sphere of positive charge must be what held everything together. And so they proposed, well, maybe it's just like from the ether. Woo! And no, that's bogus, because that would make an atom that's way too light. Like, most of the mass of an atom is not the electrons. How would we account for that? It was called the plum pudding model because it resembled a dish called plum pudding at the time, which the equivalent today would be like raisin oatmeal. So like if you had oatmeal and you put raisins in it, the raisins would float around in the oatmeal randomly, and those would be the electrons in the plum pudding, which would be the positive charge. No, we're going to move on. Then they had this model, which was like the Saturnian model, where there was a giant chunk of matter that was positively charged, and then the electrons flew around it on constrained rings. That was closer. But there's a problem with having all the rings on, or all the electrons on one constrained ring, and that is, well, if these electrons repel each other, like this, what's preventing them from just going up here and down here? Why would they stay on one ring? So there were just things that didn't work out with these theories. Or not, I guess they aren't really theories. Oh, they're kind of theories. They're trying to explain what's going on. But there's a problem with both of them. And an experiment was needed to show that these were not what was going on, and that there was some other entity. And so Rutherford came in and proposed the following. So Rutherford said, okay, we've got a bunch of ideas about how the positive part of an atom looks. Okay, so let's draw two ideas here. Okay. The first one is that the positive is in this sort of like ether, and that the electrons are just kind of floating around in it, or whatever. So there's our plum pudding model. And then the second is that we've got this solid chunk. I'm going to put like a little, like, I don't know, like a little shine to it or something like that, so that it's a solid, it's like a ball. And Rutherford said, well, here's an experiment that we can do. We have alpha particles. Alpha particles are really, really tiny. We could fire them at a sample of matter. And if the sample of matter is thin enough, we could get a very few atoms, relatively speaking, layer. The alpha particles could either pass through because the matter is soft, or would deflect off of because the matter is solid. But there is a third possibility, and that is somewhere in between these, that instead of having a large area of positive charge, maybe there was just a small area of positive charge, and that the electrons were outside of that region, like so. In this case, if we fire alpha particles at this, most of them should go straight through. but occasionally some will bounce off and then go in a random direction. And this could be any direction. But for the most part, we should be able to see a bunch of them get through here, as opposed to nothing gets through here, and all of them get through here. So the real test is going to be if anything hits on these outside regions. That would verify the third one. Okay, we have 3 different conditions and 3 different hypothetical outcomes. So let's do the experiment. This is called the gold foil experiment. Rutherford and his team of graduate students, presumably they did this in the dark in their laboratory in the 1900s, by holding up this screen in front of a box that had a radium sample in it, and they just pointed it at a sheet of gold and the detector that they were holding up, and then used their eyes to identify where things hit. Not exactly very technical, but it did the job. So here we can see that for the actual experiment, our alpha particles from the radium go to the plate being very, very thin gold foil. Gold was used because gold was probably the least chemically active metal known, and also abundant, relatively speaking. So, like, platinum is a little bit more reactive. I guess gold is probably the least reactive of the metals, so it was the most stable thing that they had on hand. And what they observed was that most of it just went straight through, so they got lots and lots and lots of activity over here. But they did occasionally see sparks at random angles. Much, much, much fewer of them, though. And so they went through those 3 choices one by one that we showed on here. Okay, well, if the atom followed the plum pudding model, there would be no way for anything to appear over here or over here, so this model was no good, because something was deflecting them. If they followed the solid model or the Saturnian model, there would be nothing over here, but there totally was. This is the model that remained. And this is the model that has withstood the test of time. We still use this model of the atom today. And so that's kind of cool that a sort of bizarre setup led to such a revolutionary method of determining atomic structure. And so I do have a video on this. There it is. We can watch that too. This one's going to get me copyright striked, but I'm going to play it anyway. Alright, so this is Backstage Science, which is a channel that does a lot of really interesting sort of experimental science and then analyzes them to a high level of detail. And what we're going to do here is I'm going to skip ahead here to the actual... It's not showing up because I've captured the wrong window. Oh, because it's captured the oil drop experiment. Yeah, that's not what I want. I want this one. There we go. All right. He looks about as excited to be here as probably the rest of us are to be here at this lecture, because Chapter 2 is super boring. But anyway. All right, here we go.
Very thin gold foil. The brass can in the center of the picture contains a small americium-241 source producing alpha particles.
This is where the alpha
Most
particles
of the
come from.
Are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the 2 detectors set up behind the foil. One of the detectors counts particles going straight ahead.
So this detector counts so F is for fixed. This is the number of particles that pass through the gold sheet and hit it square on going straight through. And so I'm going to hit play, and you're going to see that this
which
number
is the
changes
majority,
very rapidly.
and we count a rate of between 1 and 2,000 per second. The second count.
There's a second counter that's mobile and can be moved. Now, this can be spun around the apparatus wherever they want to put it.
Counter, we can move to
as you can see
measure
here.
the scattering rate as a function of angle.
So M is for mobile,
Now,
and you can see
the
that that
experiment
goes
he
much
and his
slower.
colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology.
So now what they're going to do is, instead of having a flash that you visually observe, they've hooked up the detector to a bell. And so every time an electron hits the detector and deflects, a doorbell rings. And it sounds like that.
In its current position behind the foil, it will measure one count every few seconds.
This is what working in this lab sounds like.
As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it'll just bounce straight back.
And I think you get the point. So, that's the Rutherford gold foil experiment, shown in action. And basically, this created the best model that we have today of what an atom looks like. So, instead of having a giant solid sphere or a nebulous positive sphere, we have a very dense nucleus right here. And then around the outside, this is where electrons live. Because if this guy is charged enough, its influence will reach to a certain distance and can hold negatively charged particles close enough to itself that they will continue to remain there. Just as how our planets revolve around the sun, because they are held there by the sun's gravitational pull. Let's talk very briefly about radioactivity, just so you can understand what particles were used and what they are and why they're important. So the first one's an alpha particle. The alpha particle is a helium nucleus with all of its electrons removed. Specifically, it's helium-4. There are other isotopes of helium, but helium-4 is by far the most common. Yeah, radioactivity is actually super fun. I wish that we covered this in more detail. I talk about this in Chapter 2, and then we talk about it again in Chapter 19, in 163, if we have time. Nuclear chemistry is actually super easy, and anybody who takes a basic science class could understand how a nuclear reactor works. We had one at UC Irvine, and the science behind it is like alarmingly simple. All right, so an alpha particle is positively charged, and it's relatively heavy. A beta particle is literally an electron. Beta radiation is just something that is spitting electrons at you. Now, why would this be happening? The primary reason why something will release electrons is because neutrons in the nucleus are turning into protons, and then electrons are ejected. Your friend's dad is Frederick Rhines. He has an entire building named after him, and I worked in it. That's pretty cool. Yeah, Frederick Rhines Hall. That's where all of my NMR equipment was. The rest of my work I did across the way in, what was it, Roland Hall? Yeah. Well, that's cool. It's a small world, isn't it? Yeah, I spent many days in Frederick Rhines Hall. So, where do electrons come from? So they don't fly off of the electron cloud and escape, But what they do is that neutrons in the nucleus will decompose into protons and electrons. It turns out neutrons are inherently unstable, but are stabilized when they are in close proximity to protons. This is just a little bit of nuclear physics for you. The last radioactive particle, not really a particle, is gamma ray. Gamma ray is just light, so it's a photon of energy. You can think of a gamma ray as like an X-ray, but X-rays are not as powerful as gamma rays. Gamma rays are emitted when the nucleus sort of shifts around or when it breaks apart. So if you shoot something at a nucleus and cause it to disintegrate into pieces, part of the energy release that comes from that is in the form of gamma rays. Gamma rays are very powerful per photon, and what that means is that if that photon is absorbed by something, that something gets that energy, and if there's enough of it, bad things happen. Typically, in terms of bad things for people, that means cancer. So things like, oh, a photon hits your electrons and knocks them away, and then your atom, or that atom in your body, is ionized, and it shouldn't be. For example, if you had like a DNA strand and you had an electron in a bond and you knocked it away, that bond would now break, and then other things would shift around to try and fill in that bond, and you'd get a mutation, which is obviously not good. Yeah, thermalized neutron in a 235 nucleus, that makes gamma rays. It also makes neutrons and heat. Heat is basically the important part of that. That's where nuclear power comes from, is, oh, I'm going to do stuff that makes heat. You can differentiate between radioactive particles very simply by using an electrical field. Because alpha particles are positively charged and beta particles are negatively charged, if you know the orientation of the electric field, anything that's negative is going to bend towards it, or bend towards the positive end, and anything that's positive is going to bend towards the negative end. Gamma rays, not having any charge at all, just go in a straight line. Now, why do the beta particles bend more than the alpha particles? Because electrons are light, and light things would be bent more, because the force pulling on them in this direction is going to have more impact because there's not as much mass to move. Whereas the alpha particle is much heavier and does not move as much when the same force is applied to it, despite there being twice the attraction. Okay, so now we've got a bunch of experiments that have pointed towards all sorts of information to help us figure out what the heck is going on in an atom. We can summarize all of those things together with basically a review of 140. The center of an atom is called the nucleus. Inside the nucleus are positively charged protons, and outside of the nucleus that spin around in chaotic random patterns are electrons. There's only one thing left to figure out, and that is the neutron. Excuse me. The neutron was kind of a mystery. A lot of people thought that this was it. There was a positive component and a negative component, we were done. But then we get into the isotope chemistry, and people started realizing, oh, wait a second, there's something going on here. Some of these isotopes are heavier than others, but all of the other effects are the same. What's the deal there? Now, this is summarized in your textbook as what's called as the charge to mass ratio problem. And that problem was, okay, I know how much charge is in the nucleus now because I can count how many protons there are. But for the mass that's there, I only get about half of it. The other half isn't accounted for. But it's something. What is that mass? And so the conclusion they drew was, okay, it must be matter that doesn't have a charge, but why is it there? That ends up going more into nuclear physics and how neutrons hold protons together using the weak nuclear force. Or is it the strong nuclear force? I don't remember which one it is. That's physics. It's held together by one of the fundamental nuclear forces. And so this particle right here, that's the bad color. This particle right here, the neutron, there we go. That stands out. It's kind of hideous, actually. The neutron was a particle that had no charge associated with it. And this was discovered when various scientists, I think one of them was Marie Curie, was studying radium. And I want to say that Marie Curie did several experiments and realized, well, wait a second, I have different mass sizes for my atoms that are being used here. Like, what I'm detecting is slightly different, even though all other signals are the same. And then in the 30s, evidence came along to support that, oh, okay, we can detect neutrons. These are particles that can also hit a detector, but don't have a charge associated with them because they don't bend in an electric field. One form of radiation is actually neutron emission, so things will shoot out neutrons depending on the circumstances of the matter involved. And so this led to the discovery of something called the isotope. The isotope is a collection of atoms that relate any species that have the same number of protons but different number of neutrons. So all of these shown up here on top. Oops, I hit the wrong button. These are isotopes. Specifically, these are isotopes of hydrogen. Because they all have the same number of protons. They all have one proton. There it is. But they have different numbers of neutrons. This one has 0, this one has 1, and this one has 2. If you compare any two atoms together, they have to meet this qualification down here at the bottom to be isotopes. If they don't have the same number of protons if they don't have the same number of protons, they're just different atoms. Here's a picture of the nucleus. This picture is exaggerated. The nucleus is way, way bigger than it actually is. In reality, if the nucleus was that large, my electron cloud would go out probably to Fred Meyer a few miles away. So we got the nucleus. That's the center part. This is my nucleus. The electron cloud is everything outside the nucleus. At some point, the electron cloud is considered to end because any electrons that are further away from the nucleus than that effectively don't see the nucleus anymore. Now, in my diagram here, my electrons are on little rings, but in reality, they don't follow an orbit around the nucleus. And this is because the forces that attract the electrons to the nucleus are similar in magnitude to the electrons that repel each other, or the forces that cause the electrons to repel each other. And so I'm going to draw a really simple diagram here to try and explain that. So in my little model here, I'm going to draw the sun first. And then this is the Earth. And I guess we should give the sun a smiley face too. There we go. The Earth is pulled towards the sun by gravity, and so the sun wants to kill us. But the Earth also has velocity. It's going in this direction. The end result is that the Earth goes like this, and it goes in a very regular pattern, around and around and around and around and around, because there's nothing else to really disrupt it. Now, other planets pull on the Earth. So, for example, Jupiter exhibits my Earth is not flat. I just can only draw in 2D. Here, I'll put a little shiny on it. There you go. Now it's 3D. Other planets like Jupiter, Saturn, even smaller planets like Mars, or even the Moon, exhibit a gravitational pull and want to attract to each other. But their mass compared to the sun is very, 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 very low. So by far, the biggest influence on our solar system is the sun. So everything goes around it in a rather elliptical pattern. It's very regular. If I were to look at a single proton and a single electron, the same thing would occur. I have a momentum that is carrying my electron in whatever direction it's going, and then I have the attraction to the nucleus through charge. And the result would be like this for a single isolated atom in the vacuum of space. But the second I put another electron around here, these two electrons push each other apart. And so what ends up happening is that instead of going in a circle, my atom starts to do stuff like this. Or my electron, I should say. And it ends up in this incredibly chaotic orbit that is impossible to predict. But you'll notice that what we have sort of carved out here is this region of space where the electron is likely to be found. It's possible that it could not be in that region, but most likely it's in this region. And that region is the electron cloud. Now, when we get to quantum mechanics, because it's impossible to predict where an electron is at any given time, we're going to have to rely on this model. We're going to say, okay, electrons exist in this space with 95% probability. The other 5% of the time, who knows where they are? They're somewhere else. But based on that probability, we can then make predictions about how they will behave. So that's why the nature of an electron's orbit is ridiculous and not constrained to a ring. This will come up again later in Chapter 3 when we get there. As you can probably predict, the more electrons you put in there, the more chaotic the orbit gets, because all these forces are the same magnitude, right? The difference between the electron model and the sun model is that the sun is by far the strongest thing, so it keeps everything in check. But the attraction of a proton to an electron and the repulsion of two electrons is similar enough in magnitude that it causes all hell to break loose. And that's only for two electrons. Imagine if you had like 20,000 electrons because you had a bunch of atoms that were all next to each other. It would get ridiculous really quickly. All right. What else can we talk about? Oh, because the nucleus is so small, 99.9% of an atom's volume is empty space. That includes you and all of the atoms that make you up. That includes the table you're sitting on. That includes all matter everywhere. 99.9% of it is just a void with nothing in it. Now, that brings up an interesting question. Why don't you just simply pass through other matter? That's not Photoshop. That's Photoshop. And the answer to that is, well, it's the forces that we're talking about here. If this is a table, here's my table, and then this is like your hand or something. It's not a foot, it's a hand. See, I drew the thumb. The table has electrons in it, and so does your hand. These two things push each other apart and don't allow them to pass through each other. You probably remember this interaction from physics. This is the result of the normal force. The normal force arises from what's known as electron degeneracy pressure. If you try and repel electrons into a lower orbit, they all repel each other and push back. And so everything does move, but it only moves so much because the electrons get crowded against each other, and then they repel themselves and can't be pushed any further. So, just a little more physics explanation for you. Just in case you'd never seen that. Alright. It's the strong nuclear force that holds neutrons to protons. But everything on this slide, here are our nucleons, protons, and neutrons. And then electrons float around the outside. Nothing really new or exciting there, so that's great. All right, we know how to make an atom. We know the parts of the atom. We know where they come from for the most part. Beyond that is more or less nuclear physics. So that's the extent of our discussion of what the atom is made of and how all the parts come together. Now, an important thing to note for atoms is that they're electrically neutral. That means that the number of electrons and the number of the protons must be the same, because each one has an opposite but equal in magnitude charge. We need to have the same number of each. If you don't, you end up with what's called an ion. We're going to talk about ions a lot more in Chapter 4, and also a little bit more at the end of this chapter. Chapter 4 is all about ionic bonding. We're going to look at ionic bonding in great detail. Oops, dropped my stylus. I dropped down the space bar, apparently. Okay. All right, so let's summarize everything that we covered. So for atomic theory, we've learned that all atoms of a given element are identical, and all of those atoms make up matter. Of the components of the atom, we are going to consider these three. Protons and neutrons live in the nucleus. Protons have a positive charge, neutrons have no charge. Electrons are much, 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 much smaller than protons and neutrons, but they carry the same amount of negative charge that a proton does positive charge. Changing the number of neutrons leads to isotopes. Isotopes are chemically identical but physically distinct. You can differentiate them by mass. That will be relevant to us later. And that's it. Give me a second. Let's see how many more slides there are in the next section. All sorts of slides. Okay, so that's it. We're going to stop here, because I don't want to start a new section and then just get like 2 slides into it. Okay, so we'll put this on here. I will hit this button to go back here. We'll call it a night 10 minutes early, because why not? I'm tired. You're tired. This lecture is exhausting anyway, so. Thanks for coming out to the lecture. Let me know if you have any questions. Make sure that you get those assignments done by the deadline. Did I do any work on neutrinos? No. My chemistry at UC Irvine was mostly uranium related, actually. I did inorganic chemistry. I should say that I was in Frederick Rines a lot, but I know that Frederick Rines Hall was mostly the nuclear/physics chemistry laboratory. Rowland Hall was much more chemistry focused, and that's where I spent most of my time. But I would go over to Frederick Rines to do all of my NMR experiments, so I was there half of the time, basically. Yeah, I think I knew that, but I forget what specifically it was for. All right, I'm going to shut down the stream. Thanks again for coming out. Again, make sure you get those assignments done by the deadline. I'll see you tomorrow for the rest of Chapter 2.